Hi there, welcome to another vintage computer video. So I'm sitting here next to my Heathkit H9 terminal, and if you can read the screen, I don't know how easy it is to read there, but you can see that I am playing the adventure game Zork. Don't worry, we'll get much closer to it and make it much clearer, easier to read. You might see some waviness on here. That's just a camera artifact with the CRT refresh versus the camera's photographing rate. But anyway, I sat down with this project to find out what is the least amount of computer that I could use to reasonably play the adventure game Zork. I don't know how many people remember Zork. It was a game that was popular in the early 80s, like maybe around 81, 82. Sometime in that range is when people would have encountered it. It actually has its roots tracing earlier, as early as maybe 77. But like I say, the early 80s, the PC and other computer era were where most people would have played their first adventure game. So what's the least amount of computer that you can use to do that? Well, theoretically, something that's Turing complete, like a Turing machine with a tape head and the ability to move left and right, would actually be able to play the game. But it would play it very, very slow. So let's go with something reasonable where you could have a reasonable player experience. And I settled on the Intel 4004. Produced in the early 1970s. It is a 4-bit CPU, and it had a native ROM capacity of, I believe, 4 kilobytes and RAM capacity of 640 bytes. Not kilobytes, but bytes of RAM. That's very, very small. Obviously, Zork won't fit on that. We'll talk about how we'll resolve that in a moment. But I built up this board here. And you can see here, we'll take close-ups of the board in a moment, but you can see a gold-covered IC right here. That is the 4004 microprocessor right there. There's some other things on the board, like some RAM and some ROM and a UART. But the CPU is just that little guy right there. And that is the CPU that is hooked up via this serial cable to this H9 terminal. And I am currently playing Zork on it. I will give you a walkthrough in a bit. I will also talk about the hardware that I built, and I will talk about the programming challenge of implementing Zork on a 4-bit microprocessor. Okay, I'm going to forgo the usual deep dive of the schematics for an architectural overview. So what we have here are 4 parts of the MCS 40 family. We have the 4004 CPU, the 4201 clock, the 4265 peripheral controller, and the 4289 memory interface. The RAM and the UART are both hung off of the peripheral controller, and the UART is hooked up to a DB25, which is our serial connection to our terminal. The 4289 is hooked up to the ROM, so one of the unique things about the 4004 is it treats its ROM and its RAM separately. That's why we have the RAM hooked up here to the peripheral controller and the ROM down there on the memory interface. So let's take a look at the memory interface. So this uses the 4289 standard memory interface, and it has an 8-bit address bus. Even though there's a 4-bit CPU, the memory interface will fetch in 8 bits for using standard ROMs, and it has a 12-bit address bus. So you can see I took the 8-bit data bus and I hooked it up to my 512K of flash over here in a 39SFO40 flash memory device, and I ran 10 of the address bits over there. Now that's enough to address 1 kilobyte. The other 2 address bits I ran down here to a pair of 74670 4x4 register files. You can think of these as 4 rows of 4 bits each. So these 2 bits here are enough to select one of those 4 rows, which is then output over here on this side. So this allows us to expand those 2 address bits into these 4. By cascading a second 74670, we can get another 4 address bits. And that is our memory mapping system for the ROM. Because this is addressed at 1K up here, this adds the additional 2 bits. That allows us 4 separate 1K pages. So we can take the 4004's addressable 4K of memory and split it into 4 pieces and independently map them to any 4 1K slots in this ROM over here. Now I've only got enough bits here to address 256 kilobytes of that ROM, but that's plenty for our purposes. So let's take a look at the RAM interface. Now this is done a little bit differently. We've got a 4265 peripheral controller. That peripheral controller has a variety of different modes, and one of those modes is to address a bus that has 8 address bits and 4 data bits. That's almost good enough. We'd really like to have 8 data bits. So I built this thing here I called a bus expander. It uses a couple of buffers and a couple of latches.
I went over the bus expander in my previous video on my previous 4004 single board computer, so I'm not going to go over it in much detail here. Just suffice it to say that you can take these 4 data bits and you can shift them down to be the upper 4 nibble or the lower 4 nibble over here when you're doing transfers. You just have to transfer it in 2 pieces instead of 1. That's a lot more convenient because then we can address our RAM as an 8-bit device. I used an AS6C 4008, which is a 512K static RAM. Now the address bus, as I mentioned, the 4265 only supports an 8-bit address bus, so it can only address 256 entries of RAM. So what I did is I added 3 latches. I could have gone with the same approach that I used with the 74670s that I used on the ROM, but that would have been overkill. These latches are sufficient to just let me fill in the upper bits of that address range. So these 74173s are each 4-bit latches. We can write a value to this, and that will fill in these 4 bits. That brings us up to 12 bits of address space, or we can now address 4K out of that RAM. The next 74173 adds another 4 address bits. And then the last one, I only needed 3 address bits, so it adds 3 more. That gets us up to the full 512 kilobyte range of that RAM. And these things, I programmed them the same way I did using an I/O port over here on the memory interface. So anytime you want to read RAM, what you have to do is you have to load this latch, this latch, this latch. Then you do an SRC instruction which fills in this address here. And then you do either 2 reads or 2 writes to get both nibbles out of the data bus over here. So it's kind of an ordeal to read RAM with this architecture, but this does allow us to expand from the 4004's native 640 bytes all the way up to 512 kilobytes of static RAM, which will be enough for us to play Zork.
Okay, let's take a close look at the circuit board. So first I'm going to explain this bodge wire and get it out of here so that we have a cleaned up view. And the reason for this bodge wire has to do with the UART. When I designed this board, I designed it so the UART could be jumpered anywhere from 1200 baud up to 38,400 baud. But what I had forgotten was that my Heathkit H9 terminal runs best at 600 baud. Now, the circuitry I put in there was good enough to generate that, but I just didn't have the jumper position in there. So that is the reason why we have this green bodge wire on there. Let's get that out of there so this is a bit cleaned up. And now we can go about explaining the circuit board. So this is my second 4004 single board computer. The first one here looks very similar, but with a few differences. And those differences mostly relate to the changes I made to the RAM. So on the first board, I only used the 4002-1 original vintage RAM chips. But that was only enough to get me, up to 640 bytes of memory, not enough to play Zork. So this respin of the board, which I made especially to play Zork, was designed with the 512 kilobytes of RAM in mind, which will give me more than enough RAM. Okay, so here is our 4004 CPU. He's the one chip on the board with a gold cap on him. He's a relatively small chip. You can see there's another socket around the outside, and that you could use to fit a 4040 instead of a 4004. For the purposes of this board, they're equivalent. The 4040 adds some additional features for interrupts and such. We don't need any of that, and I really wanted this to be a 4004 project. But the 4040 is much cheaper and much more readily available if someone else wants to build one. Next to the 4004, we have our 4201 clock generator and its crystal. We have a couple of the original RAM chips. These are 4002-1 RAM chips. They provide very little amount of RAM. I don't actually use them for the Zork project at all. I use the larger static RAM that I added for that. But they're in here for compatibility with the monitor program I run and other software that expected to have those 4002-1 RAM chips. This is the 4289, the standard memory interface, and next to it is the 39SF040, a 512 kilobyte flash device in a ZIF socket, so I can pop it out and replace it. Moving over here to the RAM, we have our AS6C 4008 512K RAM chip with its 1, 2, 3 latches that hold the upper bits for that. And here we have the 4265, which is that peripheral interface, which does the RAM chip and our I/O bus to the UART. I mentioned when I went over the high-level view that there are some chips that handle expanding that 4-bit data interface that comes out of the 4265 to 8 bits. That would be 2 more latches here and 2 more buffers here. Off of the data bus is not just the RAM, but also this UART over here. And the UART has this clock divider here and associated crystal and its DB25 and its level converter MAX 202. That gets us our serial. Also attached to the data bus, we have a multi-module socket that we don't actually use in this project. And we have an RC 2014 compatible bus connector that we also don't use. So I did use the RC 2014 bus connector on my previous 4004 project to hook up a front panel display. You could, in theory, run any RC 2014 module that doesn't use memory, just the I/O ones. The multi-module connector, I also used that in my previous project to do some speech synthesizers and stuff like that. That covers most of the board. I think the only thing really left to explain would be the power supply. So this here is a barrel jack, and in here comes 12 volts of power. It goes through this regulator here, which converts that down to 5 volts, because most of this board is 5 volt TTL logic. Now, I could have used a 7805 5 volt regulator, kind of a vintage, traditional linear regulator, but those things run kind of hot, especially when you start pulling lots of juice through them. So this is a switching mode regulator made by EasySBC. It's the same exact footprint as a 7805. It fits in the same space, the same 3 pins. Switching regulator runs cooler, so I tend to use those in a lot of my projects. Now, the last thing to sort out is the voltage supply for the 4004 and the other vintage chips. They require 15 volts of power. And the normal way that people do that is with plus 5 volt, so you're compatible with all of your other TTL logic, together with minus 10 volts. So plus 5 together with minus 10 will give you a 15 volt overall range. And I've got these 2 blocks here are little DC-DC converters. They're both 5 volt to 5 volt isolated DC converters. Put them in series, we get an isolated 10 volt supply. That gives us our minus 10 volts that we can use for the vintage chips, which would be the 4004, his 2 little RAM chips here, the 4289 and the 4265. We've also got a reset switch, some dip switches, some LEDs. Those are just kind of there for flavor.
Turned out to be a substantial programming project, maybe one of the more complicated vintage programming projects that I tackled, because it's in an assembly language that was pretty much new to me. And it's also a lot of assembly, and the 4004 being a 4-bit microprocessor leads to you having to break down a lot of operations into a lot smaller pieces than you would on an 8-bit or a 16-bit CPU. So to get started, I found this Z-Machine specification, and this is on a site called jaredriesinger.com. And the way that these Zork games were written was there was a language called the Zork interpreter language, ZIL, which is compiled into a assembly called ZAP, which is then turned into a bytecode that is interpreted by the Z-Machine. Now, you don't have to understand all of that if you're not a language and compiler person, but understand that all of these Zork games are written to a sort of virtual instruction set called this Z-Machine. It's made up of its own opcodes which implement the functionality. In addition to the opcodes, it also has an implicit data model where memory is divided into globals, objects, dictionary entries, and Z code that implements functions. So inside of the globals, there's various state for the game. Inside of the object tree is all of the objects that you can carry. So, for example, your lamp that you can carry, or your sword that you can carry. It's hierarchical, so objects can be inside of other objects. For example, the bottle contains water. And then the rooms are also objects. So the kitchen starts out containing the bottle, which contains the water. So already we're 3 levels deep. You've got the treasure case, I think, is in the living room. So that is another object. You could put your bauble or your gold or your chest of jewels inside the treasure case, which is then inside the living room. You can add and remove objects. So if you take an object out of a room, it goes into your inventory. You can take something out of your inventory, you can put it in the treasure case. So there's a bunch of object manipulation with this object tree that the Z-Machine needs to implement. There's also dictionary parsing that is necessary. So as you type in your words on the keyboard, something needs to tokenize those words, search them in the dictionary, find out which dictionary entry number it is, and then communicate that to the Zork game that's running inside the Z-Machine. There is a program counter, this PC that is maintained, which points at the current Z-Machine bytecode that is being executed. So you've always got to be managing that. You fetch an opcode out of the Z-Machine program, and then you increment the program counter to look at the next opcode. You can do things like calls and jumps, so your program counter can change. You also need a stack. So the Z-Machine implements traditional function call semantics, where you will call from one function to another. You need to push the return address. You need to push some arguments. So this is really, a little machine that you have to implement yourself. But the good news is, once you have implemented this machine, you can play any game that is written for that version of the Z-Machine. I implemented revision 3, and revision 3 will do Zork 1, Zork 2, Zork 3, Hitchhiker's Guide to the Galaxy, and maybe about a dozen other games that you can play using revision 3 of the Z-Machine. And inside of the instruction set is about 64 opcodes that you need to implement in order for Zork 1 to run on a Z-Machine. Things like jumps with checks. So JE is jump if equal. So given two operands, if they're equal, jump to this label. Jump if less than, jump if greater than. Decrementing and incrementing variables. Managing the attributes with the objects. Getting and writing memory. Managing the properties with the objects. Math, like adding, subtracting, multiplying, dividing. Don't even get me started on how difficult it is to write multiply and divide on a 4004. Various things for getting siblings and children, inserting and removing objects, printing things. So Zork uses this weird packed format. The same packed format I mentioned for the dictionary lookups is used for printing strings. So it chunks text into 5-bit characters. It sticks 3 of them to a 16-bit word. It uses shifts so that you can do uppercase or letters or symbols. And then you have to decode all of this and print it out. Well, as I mentioned at the beginning, the 4004's address space is really very limited. There's only 4 kilobytes of RAM that it can natively address, but I divided the address space into 4 1-kilobyte pages. I reserved 3 of those pages for shared common functions, so things like doing the serial I/O or manipulating the program counter or calling across to other pages or reading and writing global variables and stuff out of RAM. That's all in this common 3 kilobytes of core pages. But that left me 1 page up here that I was able to use to page in various things on demand. And that's where most of the Z-Machine implementation is. The first 111 pages are responsible for loading the data from ROM into RAM, because parts of the data that comprise the game are modifiable. So all of the objects might be moved around, their properties might be changed, the global variables can change. It's most convenient just to copy the whole lot of it into RAM so that we can then modify it at will. Now, there's some idiosyncrasies about how you access ROM on the 4004 that led me to put 768 bytes of Zork data per 1 kilobyte of page. So it took me 111 pages, 768 bytes of data stored on each page, and that leads to about 84 kilobytes of Zork data, which is the size of Zork. So the first thing that the Z-Machine will do is copy all of that stuff. And then after copying all of that stuff, it jumps into run. And run is the workhorse routine that handles fetching the opcodes out of memory, fetching the operands for the opcodes, and then deciding which subsequent page to call. And there are a bunch of other pages that implement those opcodes. One of those opcodes is called read. And read is responsible for reading your input from the keyboard and filtering out disallowed characters and converting everything to the same case and handling the backspace, handling the carriage return when you're done. And then the next thing read does is it jumps to an internal routine called parse. And parse encodes the words you typed separated by spaces into those 16-bit, 5-bit encoded text things that Zork likes to use, looks them up in the dictionary, and then stores each word number in a list, which it hands back to the Zork program, which then decides, how to execute what the user has asked for. There are all kinds of other opcodes. So, there's a page dedicated to jumps. There's a page dedicated to prints. There's a page dedicated to calling things. There's a page dedicated to math, your add, subtract, multiply, divide. A page for bitwise operations. A page for doing stuff with properties of objects. A page that handles things like getting random numbers. All of those are additional pages. And like I said, when run wants to run an opcode, it figures out what pages it's in. It jumps through the paging function down here in the core, which will page in this and jump into there. And then when one of these things is done, it jumps back through the paging function and goes back into run, where run will look for the next opcode. So that is the basics of how my Z-Machine was implemented on the 4004.
Okay, let's try a walkthrough of a few commands into Zork. So I have the board is over here. It's hooked up to my Heathkit H9 terminal. Now I chose this terminal because it is the oldest, most primitive terminal that I have. This thing actually has no CPU in it whatsoever. It's implemented with TTL logic. And it's only got about 12 rows and maybe 40 columns wide, but it'll be good enough to play Zork, and it'll be something reminiscent of what you might have been able to have back in the day. So I'm going to boot up the 4004 board, and there we've got the menu that comes up from the single board computer. This monitor was originally written by Jim Luce for his 4004 project. I adapted it for mine, and I've put Zork in bank D. So let me push the D key, and now we can see it's printing these dots. This is while it is copying Zork from ROM into RAM, because I play it out of RAM, but we've got to copy it all in there. So it loaded it into RAM, and now it's executing the bytecode from the Z Engine compiled file. You can see here it has printed the initial screen of Zork. We're west of house. You're standing in the open field. There's a small mailbox. We can open the mailbox. And you can see it's not the fastest thing in the world. This is a 4-bit microprocessor after all, but it is actually usable. Let's read leaflet. Takes it a little bit of thinking here. We picked up the leaflet, and we're printing out some text. Now let's do south. East. Now we are at the window. Let me open. Whoops. There's about open window. Enter. Where's my rub out? This keyboard is not the most usable thing in the world. That's one problem with the H9. Enter the window. We are in the kitchen. We'll just take this to the point where I can get us killed, because I love getting killed in Zork. There we go. West. Move the rug. You notice I am not picking up the lantern. That will turn out to be a fatal mistake in a moment. In case you're wondering about the speed of the terminal, this is about 600 baud. Open trap door. Down. Oh, it's a dark place. Someone has barred the door above us. We could be eaten by a grue. Let's go east. Uh-oh. There was that grue they were talking about. Well, we are dead and we are respawning. So that was just a quick playthrough just to show you how fast it is on the 4004. It's, like I said, it's not the fastest thing in the world, but it is actually playable.
Okay, for the final part of the video, what I've done here is I've connected the board up to a terminal program on my PC, where I'm going to run a complete walkthrough of Zork from start to finish, all 350 points. And I did this by pre-recording all of the winning moves into a file, and I'm playing the file through the terminal emulator. So you'll be able to see the whole thing run through. Now, I timed this. It takes 1 hour and 39 minutes to get through it. And I've sped this up because we don't really want it to take that long, but I just wanted to demonstrate that the was fully capable of executing every command necessary to win the game. You'll notice at the very end that when we print out the score will be printed in hex. And the reason I'm doing that is because printing out base 10 numbers is a little bit more difficult, especially with the limited multiply and divide functions. So I went ahead and I just printed out my numbers in hexadecimal instead of decimal.
Okay, I hope you enjoyed this video of me demoing my single board computer here running the Intel 4004 4-bit microprocessor, playing Zork on my Heathkit H9 terminal. Thank you. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.